All right. Today's notes are all about conservation of momentum. It's a very straightforward topic, and as such, we only have one objective, which is to describe how momentum is conserved in a closed system. So let's just jump right on in. All objects in motion have a property called momentum, and sometimes those objects interact with each other. When isolated objects interact, then the momentum of that entire system is conserved. Isolated is just describing what us physicists like, which is where we're pretending that no other forces are acting on this object, which includes things like friction and air resistance. Okay, so as usual, we are going to pretend friction is not a thing here when we are learning about this concept. Okay? Conservation of momentum can be written in two different ways. The first is total initial momentum is equal to total final momentum. Or you can actually write out each of those. Remembering that momentum is mass times velocity, we can do mass of the first object times the initial velocity of the first object plus the mass of the second object times its initial velocity is equal to the mass of the first object times its final velocity and the mass of the second object times its final velocity. Imagine two different interactions to help illustrate how this works. Momentum is going to be conserved in collisions. If you have a stationary billiard ball and it is hit by a moving billiard ball, then both balls are going to experience a change in velocity and thus a change in their individual momentums. The momentum that is gained by the stationary billiard ball is going to be equal to the momentum that is lost by the ball that struck it. So, as a whole, the system itself loses no momentum. It's just transferred from object to object. Of course, we know in a real world there is friction involved here, which means loss of energy, which means loss of momentum. But in an ideal situation where there was no friction, the momentum would be the same. If you were talking about the momentum of both balls combined before and after the collision, it should be the same. In addition to this, momentum is conserved for objects that push away from each other. So imagine you and your friends are standing on an ice rink, because an ice rink is as close to frictionless as we get here on Earth. Okay? And you are starting from rest, and you push off of each other, and you move in opposite directions. To begin with, neither of you were moving, so your momentum as a system was zero. You had no momentum, your friend had no momentum. So you're saying, how is it possible then for us to still have a momentum of zero when we are obviously going to be moving at the end of this? Well, you have to think about the fact that you are, but because you are moving in opposite directions, your momentums are one of you positive and one of you negative. So as a result, they're going to cancel, and the net momentum for the system will remain zero. Let's do an example problem using this lovely concept. We're going to pretend that there is a 76 kilogram boater who is initially at rest, and he's at rest inside a stationary 45 kilogram boat. So both the boater and the boat are at rest. He steps out of the boat and onto the dock. When he's stepping out of the boat, his final velocity is 2.5 meters per second to the right. So, what must the final velocity of the boat be? Go ahead and try this out, and then we'll work through it. Okay, we're going to take that equation that we had the nicely written out one where we had mass of the first object. In this case, we'll say the first object is the boater times the boater's initial velocity plus the mass of the second object, or the boat, times its initial velocity. Sorry, that should be. It's going to equal the mass of the object times its final velocity plus object 2 times its final velocity. One nice thing is that we know that these two quantities over here are 0, right? Because initially the boat is at rest and the boater is also at rest, which means neither of them have any momentum, which means to begin with, this whole system has no momentum. So we know that these two pieces over here are going to have to be equal to 0 when we end this. So we can go ahead and just set them against 0 to make it a little easier for ourselves. So mass of object 1 times velocity of object 1 final plus mass of object 2 times velocity of object 2 final is going to be equal to 0. And then we can simply either plug our information into this and solve it, or we can go ahead and try to isolate this variable, get it by itself, which is what I'm going to do. Requires us subtracting this from this side, right? And then we get, velocity initial final. And then we're going to wind up with something that looks like this. And we're going to divide both sides by the mass of 2 so that we wind up with our equation being the velocity of the second object final is going to be equal to the negative version of mass 1 divided by mass 2, and that's going to be taken times velocity 1 final. So now we can just plug our numbers in to that particular equation. We'll have velocity 2 final. We know it's a 76 kilogram boater. We need a negative sign here. And we know it is a 45 kilogram boat times 2.5 meters per second. And that is to the right. So when we do this math, what we should wind up with is negative 4.2 meters per second to the right. We could just report negative 4.2 meters per second, or we could instead erase the sign and say that it was to the left. Either option is acceptable. All right. The last thing we're going to do is make a connection between Newton's third law and conservation of momentum. So imagine the billiard ball example again, but this time, instead of writing it using the mass times velocity, we write it using impulse momentum theorem. Ball 1 would have the following equation. force of 1 times change in time is equal to mass of 1 times velocity final of 1 minus mass of 1 velocity initial. And ball 2 would have this equation. It looks identical. We've just substituted in the correct variables. Because of Newton's third law, we know that the forces of two objects pushing on each other are equal in magnitude but opposite in direction. So that means that we can have them happen over the same time change. Their impulses are equal but opposite, which gives us the following equation. Force on the first object times change in time is equal to the negative force of the second object times change in time. The changes in momentum are then going to be equal in magnitude but opposite in direction. This means if one momentum increases, then the other momentum must decrease by the same amount, which we already discussed as being a real reality in our billiard ball example. You can't have momentum come from nowhere. If one object is gaining momentum after a collision, the other object must lose it. So you can write it this way. Mass of object 1 times velocity final of object 1 minus mass of object 1 times velocity initial is equal to the negative of the mass of the second object times its final velocity minus the mass of the second object times its initial velocity. So we're looking at changes in momentum. Basically saying this minus this is saying whatever the change in momentum is. And we can rewrite that as our original equation for conservation of momentum, which shows you how very nicely Newton's third law complements our change in momentum or conservation of momentum law. In real life, unfortunately, forces are not constant during a collision. What tends to happen is as one object begins to exert a force on another object, you have an increase in force all the way up until a peak, and then a decrease in force. So it's not this constant, 5 Newton force the whole time. It might start off as a 1 Newton force, ramp up to 5, and then back down off of 5. It's not going to be constant the whole way throughout. Unfortunately, that would make it very difficult to run calculations in physics. So when we run them for these theoretical problems, we're going to be using the average force instead of this changing force. So it will be the force required to cause the same change in momentum over the same period of time as the actual changing force. So it's just an average, just like we would use average speed rather than instantaneous speed in other problems. All right, that should be the end of our notes.